Dear fellow coders, welcome to Untitled Coder. This is day 14 of Kaggle's 30 Days of Machine Learning Challenge, and in this video we are going to learn about XGBoost and data leakage. We already spoke a little bit about data leakage in the previous video, so if you have not seen that, that might give you a little bit of introduction. And in this video we are going to learn a little bit about XGBoost and then hyperparameter tuning, and also a practical example of using XGBoost. And this is probably the last two sessions of intermediate ML course, and after this session finishes we are going to implement whatever we have learned in a live competition or exclusive competition, that's what they're calling, to see how we perform in the competition where we have with the things that we have learned so far. So let's just get started with XGBoost. XGBoost stands for extreme gradient boosting. It's a variant of gradient boosting. And now gradient boosting belongs to a family of methods called ensemble methods, where you combine multiple models and then arrive at a better model. So that's the idea that you have got. If you remember a random forest that we have used in the past, so that is where we have built multiple decision trees and then we averaged out the final predictions and got the result. So which we said is a better way of getting a higher accuracy than having a single decision tree. There are some counter arguments that somebody might make why you shouldn't use ensemble methods, but we will leave those out of discussion as of now. So now looking into gradient boosting. So now what is gradient boosting? A simple introduction we'll see what is gradient boosting. The name gradient is inside boosting along with boosting is because gradient boosting uses a method called gradient descent for a particular step. So that's why gradient boosting. Otherwise, the family of boosting methods, like I said, it's part of ensemble method. So what happens in a typical boosting model or method is that you first initialize a single model. So there is like an ensemble, like a group of models, let's say. So you first initialize with a single model. Okay, so that's mostly called like a weak learner. And that weak learner, it's called weak learner, of course, because it does a terrible prediction. So it's pretty naive. The predictions are pretty naive, and you know that it's inaccurate. But the whole idea is how do you improve this model step by step in such a way that in every step you minimize the error. So first you have got a single model in your ensemble and who's got like very weak predictions, and now you are going to use this single model that you have in your current ensemble, or just simply say current ensemble, and then you're going to make predictions against each observation in the data set. Like if you imagine like you have got 5 data points, for all the 5 data points you're going to use your current model and then make predictions. And then the predictions that you have got, that prediction you're going to use and calculate a loss function. Loss function is nothing but like your mean squared error, like an evaluation metric like RMSE in terms of regression. So that's what your loss function is. So for example, if you make it for 5 prediction, let's say your mean absolute error or mean squared error could be somewhere around, let's say like 0.7 or something like that. Let us assume that there is an error. Now that you have a first set of prediction and you have a first set of error for that, now you are going to use the loss function, the output of the loss function, like whatever that error that you calculated, to fit a new model that will be added to ensemble. So now this loss function, whatever you calculated, that's like a new feature, whatever you calculated. So now you're going to build a new model that will also take the loss function into account. And then the way the new model is built is to reduce the loss, like reduce the error that you already have got. And then the method that we use to do this, which is also called an optimization problem, is gradient descent. Gradient descent in simple term is like trying to find the minimum, local minimum, like the global minimum, where like if you actually think that you're trying to find the best answer, so it's like you use gradient descent. It's like an optimization algorithm. So every time you try to find the best way to build the model so that your loss is the least in that iteration, and then you just add the model and then you repeat the whole process. So first you start with a single model, then using your current ensemble, you are going to make some predictions. Using that prediction, you're going to calculate some loss function. Now using that loss function, you're going to create a new model, like fit a new model and add it to ensemble. And the way you build a new model, you're going to use gradient descent to make sure that you minimize the loss, minimize the error, So the next step is finally you are going to add the model to the ensemble, and finally you are going to repeat the process. So naive model, make predictions, calculate loss, train the new model, add the new model to ensemble using gradient descent in such a way that you have minimum error. So this is a very naive introduction, I would say, about XGBoost. I don't do enough justice in explaining this. So I would point you to one of the most popular machine learning tutor on the internet, StatQuest with Josh Tarmer. So you would see bam, bam, bam everywhere. So this video, which I would also link in the YouTube description, is really an absolute amazing explanation of XGBoost, separately for classification, separately for regression. You should definitely watch. It doesn't take a lot of time. So this is again very handy if you're going to prepare for interview, if somebody is going to ask you in-depth questions, or even for you to get the intuition about what is XGBoost regression does. So again, the way I explained is quite naive. You should definitely check out this YouTube video by StatQuest with Josh Tarmer, and that would give you a better idea about it. So now that you know where to go and learn more about XGBoost, so now until now what we looked at is gradient boosting. So what is XGBoost? XGBoost is a variant of gradient boosting, which is called extreme gradient boosting. It's a separate implementation that has got a couple of advantages like performance and speed. And of course, like if you have been following Kaggle competition, XGBoost was the undisputed king for quite a while. A lot of Kaggle grandmasters used to win using XGBoost, and XGBoost was quite popular when Kaggle used to have a lot of tabular competitions before even the start of like Light GBM, Cat Boost. Like before even these models came in, XGBoost was like really the king of Kaggle competitions at that time. So there are some advantages of XGBoost and how it differs from gradient boosting. You should definitely check out that video and then you'll get understanding. So for gradient boosting, especially if you want XGBoost, there is a separate library called XGBoost, and you can try that. Like for example, from XGBoost you can try that. Within scikit-learn there is a gradient boosting function as well. So like if you want, you can check that, but usually people use the XGBoost from the XGBoost model like library. Okay, so now from XGBoost import the class XGBoost regressor and then create an object my model and then fit. So the process is same. So you import, define, fit, and then predict, and then finally you evaluate. So now if you want to make prediction, like you have so this is the output. So what you actually see in this is when you initialize this, these are all the default values of hyperparameters, the parameters that you have got, all the default values that the model has already assumed that this is what you want basically, and then it has created this model with this. So this is more like a baseline model. That's what it's usually called. So you don't give any parameters and then you just go with the default values. But in the future section we are going to see some parameters and then how we can optimize and what does it mean. Now that we have defined the XGBoost model, let's just make a prediction. So again, we have defined it on an object called my model, and when you use mean absolute error MAE to predict the model, and then if you see the score, so it's around 238,794. so this is the MAE that you have got using baseline of XGBoost model. Now what we are going to learn is how you can fine-tune few parameters using XGBoost that can actually have a huge impact in your accuracy and training speed. And that's why XGBoost is actually very popular, because one, it gives a very good score in baseline model itself, but again, like you have the ability to actually fine-tune a couple of things that can ridiculously improve your model accuracy. So first thing is number of estimators. Number of estimator is nothing but number of times you're going to actually do this process, which also means number of times you build this model. So it's like number of models. Number of estimators is almost like number of loops, and then which is basically your number of models. So when you use number of estimators, so you can set a value from typically from 100 to 1000. So you should keep one thing in mind is, if you keep a lesser value for number of estimators, which means you are basically building very less number of models, which means your ensemble is not much of an ensemble, because you have very less number of individual models that too are weak learners. So ultimately you are going to underfit, because you do not have enough models for the predictions to become good. When you have a lot of models, then you should probably know the opposite of underfitting. It's overfitting, so it's going to end up overfitting. So like that's why it's a very important to settle with something that that is in the middle ground. So typically people set from 100 to 1000. Again, depends upon a lot of factors, your computation power, and also another thing that we are going to learn in the future section, which is learning rate. So number of estimators you can train, and then you can define a model like this and do. Another important aspect, if you are confused about number of estimators, is called early stopping rounding. What does early stopping rounding is? To say when do you want to break this loop, how long you want it to keep on building it. So early stopping round is nothing but a validation strategy where when your validation score does not go up or doesn't improve, I should say, when your validation score stops improving, so you are telling the model automatically, you're defining in the model defining stage itself that when my validation score doesn't improve, stop it. But how long you want to try that before that is what your early stopping round is. So if you set a very high number of estimators, and then if you use early stopping round, then you can say that, okay, probably I've tried to overfit the model. Maybe like that's what happens when you set a very high estimator value, but I'm going to stop that overfitting by using a force, which is early stopping round, which is like when my validation score does not improve, then it will stop iterating, it will stop looping. So for example, like you can set very high score, like number of estimators like 500, but you can actually use early stopping round like 5. So maximum it will go till 5, and it might stop after that. So this is like a combination. And when you set early stopping round, it needs to validate against some validation data set. That's the whole point, right? So it's going to evaluate against a validation data set. When the score doesn't improve, then it's going to stop. So for that you need to give an evaluation set as well, eval set. So that's what you're doing. And verbose equal to false, so that you don't get to see like how in movies they show some computer engineers hacking a machine. So otherwise you would see validation score, or your train score, validation score, train score. So you would see a list of all these things getting printed. If you don't want that to happen, you can just say verbose equal to false. But many people like to keep it open, so they get to see what is happening. And that is how you actually do this. So if you know that you have the optimal number of estimators, and then you have also the value for early stopping round, then what you can do is, now you are actually building it on validation data set, right? So you like after like part of cross validation. So finally, when you want to test it against or predict against the test data set, you can actually set number of estimators, like whatever value that you found optimal in this process, and then with the early stopping. So that way your model, you have got the best model to predict against the entire data set. And now what is a learning rate? A learning rate is nothing but like a variable that will say how fast or how slow you should move every time you make a prediction. So to explain you slightly mathematically, so if you get predictions, what you would usually do is you would start adding up the prediction from each model, and then you would start using it. But what if you have like a weightage factor, or what if you have a multiplication factor that can actually give weightage to every prediction from like each model? So that's where you use like a very small number learning rate before you start adding them. Like it's like 0.3, 0.05. So which means like every time you get that, so you use that learning rate to as a like a multiplication factor, and then you add the prediction. So what does it mean? It means if you have a very small learning rate, it will take a lot of time for the model to converge, like for it to find that best ultimate model. If you have a large learning rate, like 1 or something like that, so there is a very high chance that you might miss that convergence, and your models just keep on happening, because the early stopping would never happen, because your validation score never like that overfitting thing never happens. So it's like a combination of these things that will help you decide the right XGBoost model. So what we can usually do is we can set a very higher value of n estimators, number of estimators, and we can use early stopping to decide the number of trees, and then we can actually set a very like a decent learning rate. So like we have a combination of all these things. So in general, a smaller learning rate and a large number of estimators will result in accurate XGBoost model. But a smaller learning rate means it will take a longer time to train, because every iteration, the addition, if you see that you have that multiplication factor. So by default, XGBoost sets a value of 0.1, but you can change it based on the need that you have, like the computation population you have, like the time that you have. And finally, n jobs basically says number of parallel jobs that you want to run. Like we said, again, XGBoost helps you in XGBoost is again used heavily in real production environment in a lot of companies. So in job, when you use that, it helps you parallelize the process, the model building process. So basically you equal this to the number of cores on your machine, like depending upon what kind of computer that you use. And again, another important thing is it might not help much in a smaller data set, because what will you parallelize when you have a very smaller data set, right? So it is usually helpful in a larger data set. When you have large data set, when you want to parallelize, it's like you can imagine like the single node map reduce, something like that. It's not exactly like that, but I'm just telling you, it's more like parallelizing your process in such a way that all of your cores are fired up, like maximum use, and then you get the result faster than using single core. That's the whole point of having multiple core as well, right? So it takes advantage of that. So if you have larger data set, leverage this. If you have smaller data set, just don't use it. So now at this step, like we know like what do we do with the number of estimators, we know what do we do with like learning rate, and we know what do we do with the number of jobs as well, and when we have to use it. And we also know that when we use early stopping, we need to also give evaluation data set. And usually if you do not give verbose, you just get the model value get printed. But when you use verbose, you get to see the training and validation data as well. To conclude this, so XGBoost is really popular. So even you can go to the very recent Kaggle survey, Kaggle 2020 or 21 survey. So you would still see XGBoost being used in a lot of cases. XGBoost is still popular in a lot of tabular competitions even today on Kaggle. So there was a paper recently that said compared XGBoost against a lot of deep learning frameworks for tabular datasets. So XGBoost is really good for tabular dataset even today. So the better you know XGBoost, the better you can maneuver your work life if you're going to be a data scientist who uses XGBoost in real life. And again, the advantage with XGBoost is it can work very well in production. A lot of companies use it. If you want to improve your score, very few parameter tuning can help you improve your XGBoost accuracy. There are a lot of different strategies for that. Like one is like how we do, looking at the cross validation and then improving. Another is like there is a very popular concept called grid search. You can also search about grid search, and then learn how you can use grid search to improve your XGBoost model, to find the best XGBoost model. Okay, so XGBoost is really important. You can use it, like just close your eyes and use it. One thing that is probably not covered here, maybe it's in a different class, is interpretability. So usually there is an argument that models like XGBoost, like random forest ensemble models, may not be very good in interpreting a model. Like what is happening with the model, how is the model predicting, can I understand the individual logic behind the prediction. So this is the usual argument that is made. So I just quickly wanted to show you that XGBoost feature importance. So but the solution to this, and also like a lot of times business would want to know how you have made a particular prediction. So there are multiple ways to get feature importance from XGBoost, which means when you make some prediction, XGBoost can actually tell what are those variables, features, dimensions that contributed most to the prediction. So what is like if you look at something like what is the thing that most contributed to predicting your outcome variable, like target variable. So XGBoost can help you in that. By default, XGBoost has this feature importance plot which you can make and then get the answer. But but there are other solutions like SHAP. I would say SHAP XGBoost. SHAP is again quite popular. Line is another thing. So if you look at SHAP, you can see like SHAP will give you something like this, will help you understand at overall interpretability at a global level, interpretability at a local level. So again, I don't want to get into that topic much. Probably Kaggle has planned this already, but just what I wanted to share is that a lot of times you might see this argument that models like random forest and XGBoost are not very good for interpretability, but there are a lot of good solutions available these days that can help you in understanding. Maybe it is not that explainable like your linear regression or logistic regression where you've got simple coefficients, but you can still offer XGBoost model explainability. So that is another topic that you should definitely check out. Model explainability, grid search, and then also go to the stat quest video and then learn about XGBoost. So these are your 3 action items. After this, again, do your exercise. I'm not going to do the exercise. Do your exercise, and then it's quite simple. Just implement it in the data set that we have already been using, the Iowa data set. So that takes us to the end of XGBoost section, and the final section in this is a very important concept that often very much ignored. Thanks to Kaggle for putting this together. Concept that is very often ignored while anybody is teaching you machine learning, which is called data leakage. We saw data leakage in the previous video when we were discussing about why to use a scikit-learn pipeline. But in this video, in this section, we're going to see a little bit in depth about data leakage. Not so in depth, but a little bit in depth. So now, what is data leakage? Data leakage or leakage is quite simple to explain but very hard to detect, and it's often unknown. That might ruin your model in subtle and dangerous ways, and it's one of the most important concepts practicing data scientists should learn, but often they do not. So that's a concern. So now, what is data leakage? Data leakage can come in 2 different forms. One is called target data leakage. The second is called train test contamination. So depending upon what type it is, the definition might change. So basically what happens is data leakage means that your training data somehow contains an information about a target that ideally should not be there. And when you usually use model validation, even cross validation, because of that subtle information that is present in a training data set, which is ideally not supposed to be there about your target information or test data set, this might make your model look that your model is actually doing on both training data set and even on validation data set, but 100% it will do bad on it will perform bad on your production data set, or like on Kaggle's term, that your model might do good on your training data set, your model might do good on your public leaderboard, but it might perform bad on your private leaderboard, because again, that's a whole lot data set altogether. So this is what data leakage is, and this process of this thing happening is data leakage. So in other words, basically a leakage causes model to look accurate until you start making decisions with like a real world data set. So it's like overfitting that you cannot even catch with your cross validation strategies. Like we saw, there are 2 types: train leakage, train test contamination, did I say train leakage? So target leakage and train test contamination. Target leakage is quite simple to understand. Basically, like you have a target variable which you are trying to predict. So there is some column, there's some variable that is a feature that is there in your data set that is like a proxy of your target variable. So there is a target variable which you are going to ultimately predict, but there is some column in your feature in your training data set that is like a proxy. And that proxy, because of that proxy, when you include that proxy in prediction, so that might actually make your predictions look good even on validation data set, because that proxy exists on validation data set as well. But mind you, that proxy may not even be available in your real world data set, and even if that proxy is available, that may not have the same information. So let's quickly take a look at an example, so that might give you some idea. So we have got a tabular data like this. So whether somebody has got pneumonia, that's a Boolean value, age, weight, gender, and whether somebody took an antibiotic medicine. So now you're trying to predict this column which has got pneumonia, which is like a classification problem now. So you might use all the other columns, and you might even get a good accuracy. But what you may not know or realize is that This column took antibiotic medicine is a column that is usually marked after somebody got pneumonia, which means somebody would have taken antibiotic only if they have got pneumonia. That's what you could see. Also, like whenever pneumonia is false, took antibiotic is also false. Whenever pneumonia is true, took antibiotic is also true. So now when you use this setup for your training data set, it would look good on training validation, score evaluation. It would look good on validation evaluation, because that's like this column exists there as well. But when you actually deploy it on production, how will you get this value? Maybe because like before anybody gets pneumonia, for everybody this value is false, so or maybe the data doesn't exist. So it is possible that this model would it is possible, it's most likely that this model would perform very bad in real world data set, because it has actually used something that is not supposed to be there as a very important variable to make this prediction. So basically whatever this model has learned is actually bad, and it will result in inaccurate predictions if it is deployed, and especially when you are going to use it for such costs, then you have to be very careful. So to prevent this type of leakage, any variable updated after the target value realized should be excluded. So if you know any variable that is usually created after the target variable or because of the target variable, that should be excluded from the model training process. So you can just say like leakage variables to exclude. So that's very important thing. So the next thing is train test contamination. We'll see an example in the future section. The next section is train test contamination. This is what we discussed in the previous video. So where instead of a proxy for a target variable, what happens is you might split train and test after you do some data processing, and because of that data processing, that some information about your test data, which is your validation data in this case, is present in your train data, and then your model has picked that up. And because of that, you might get a very good score in a validation data set, but it might still do worse in your real world data set that it has not seen, like a test data set. So again, let me just say, you have got training data set which you are going to split into train and test, which is in this case is validation, and then you're going to build the model. But what you might have done without knowing is that you might have done pre-processing, like fitting imputer, like filling in missing values using the whole data set. Now when you do split, your training data set and validation data set are two different data set, but inadvertently, so your test data set's information is present in training data set in the form of, let's say, mean value, median value, or something like that. Now because of this, your model has learned something that is available only in your test data set or validation data set in this case, and your validation score looks good. You might think your model is not overfitting, but indeed it is overfitting, and you couldn't catch it because your validation score is good. And this kind of thing is called train test contamination, which usually happens because you did not have the right cross validation strategy, or you are not very clear about how you did the split. And one of the easiest way to avoid this problem is to use scikit-learn pipelines. And it is very important for you to use scikit-learn pipeline when you use cross validation, because otherwise there is a very high chance that you might make some mistake, and then because of that mistake you might contaminate your train test that split when you do. And a very quick example for us to see, let's look at a data set about credit card application, and when you see the data set looks like this. And what we are trying to predict is whether somebody whether the application is predicted, like when somebody submits your credit card, whether the application is predicted. So this is how the data set looks like. So y is like the card value, whether the data set is accepted, and we have dropped X. So this is basically how it looks like. Now what we can do is we can actually make a pipeline like we learned before, and then we are going to use random forest classifier, and then we are going to use cross validation. Make a pipeline with this. We are not doing any pipeline, like we are not doing any we are not using the pipeline class because there is no pre-processing. That's why we are using make pipeline, and then we are using that object, and then we are using X and Y, and we are going to get a score. The moment you get score like 98% accuracy, probably this is the time you should automatically know that there has something terribly gone wrong, rather than celebrating that, wow, I've got 98% accuracy, and then start publishing this on every presentation that you have got in your company that my team has got 98% accuracy. You should probably by this time realize that something must have gone wrong, because it's not very easy for you to predict something in real world that is like 98% accuracy. Can you believe it? 98% accuracy. So now when you start looking into the data, so you have got the data dictionary, where you get information about every single, and you can actually notice couple of variables that might look suspicious. For example, if you look at expenditure is a average monthly credit card expenditure. Now imagine if somebody had not even got a credit card accepted, how can you even have this column, right? I mean, like, if I do not have a credit card, if my credit card was not accepted in the first place, how can I have it? I will not have it. So this column is now something that this column contains the information that it can actually talk about whether you got credit card or no. So now if you compare this column, like a fraction of those who did not receive a credit card and had no expenditure, and 100%, if you compare the fraction of people who had received a credit card and no expenditure, so that is very minute. So you can see only 2% who received a credit card had no expenditure, but 100% people who did not receive a credit card also had no expenditure. Now the thing that you should ideally do is you drop the columns that can potentially have leaky predictors, like expenditure. Share is another thing. Active is like number of credit card accounts. Share is like ratio of credit. And then what other column? The column is major cards, which is like number of major cards currently held. So all these columns are filled. See, you are getting a data from somebody had already stored. So the person who stored the data is not going to think that you're going to use it for machine learning model. So it's your responsibility to make sure that you know that. So probably these columns were filled after somebody got credit card. So if I use this, I'm basically trying to use future data and then trying to predict something in the past. So it's like, you've got a cricket match score tomorrow, and you already know somebody is winning, like let's say India is winning England, and then now you use that information to predict something that is going to happen today, saying like, oh, maybe Virat Kohli is going to declare at this moment. So you are basically using a future information and then trying to predict the present, which is of course would work in your training and validation data set, but when it comes to your test data set, it may not work. So that's why you should remove that. And when you remove that and you do the same thing, your validation accuracy has come down to 83%. It might feel bad to look at an accuracy like that, but you should be very sure that this 80% accuracy would work well even when I try it on my even when I try it on the production data set, like a real world data set. So that's the main thing. So this might be slightly disappointing, but we can expect it to be right about 80% of the time when we use it with like real world data set that we have never seen. But when we had used this model, like even we have seen 90% accuracy, it would have done definitely terrible on your external real world data set. That's a very important thing. Data leakage can become a multi-million-dollar mistake, as they say, because it might have a lot of problems. So important things to notice: carefully separating train and validation data set can prevent train test contamination. Use pipelines so that again you would tend to avoid this mistake. And then the other thing is always try to find columns, like understand your predictors, and then identify which one could have could be a proxy of your target variable, and then try to avoid that. So that's why business knowledge is quite important here. A lot of Kaggle competitions, if you actually see, because of data leakage, a lot of times a lot of things go for a toss. Sometimes the company would would give you new test data set. Sometimes a lot of things have happened. Data leakage is something that has happened in Kaggle competition over and over again. So what I'm trying to say is, even if when you try to carefully craft something, still data leakage can occur. So in your workplace, you should always remember that data leakage is possible, and then you should try to avoid. Once again, there are very good examples where you can see how data leakage you can avoid, and then how to identify. So definitely do this exercise. Once you do this exercise, you must have already done all the exercise. You would get a certification from Kaggle that you have successfully completed the intermediate machine learning course. So if you do all the exercise, which I'm not in my case, so if you do all the exercise, then you would get 100% progress, and then you would get the certification. So I hope you get the certification. That's like a token of appreciation for what you have done. And to quickly summarize what we have learned in the intermediate machine learning, we have learned a quick introduction about what we are going to do, how to handle missing values, how to handle categorical variables. Once again, if I have to just say, random forest, XGBoost are models that can itself handle missing values, but if you handle it yourself, there's a very good chance that you know what is happening, and then you can explain it to your stakeholders as well. And pipeline, again, a lot of good advantages with pipeline. For example, clean code. One important thing that we saw is like how pipeline as a procedure would help you avoid the train test contamination, which is part of data leakage. Cross validation, very important, so that your model generalizes. We also learned about a new XGBoost model. Definitely check out StartQuest video. And then finally we got a slightly deeper into data leakage, and that takes us to the end of intermediate machine learning. So Kaggle has said that now that we have learned this thing, so over a couple of next couple of weeks, we'll actually apply it in exclusive competition that is open only for people who signed up for the program. So I need to figure out how people who have not signed up for this program can join. That's what I think most of you are. So if you have any questions, please let me know in the comment section. Otherwise, try to do this exercise actively, take part in Kaggle discussion. That might actually make a huge difference. Don't just do it for this 30 days of machine learning. Think long term. It's always good to have a good Kaggle profile, good Kaggle rank, and good to be part of the community where you can learn from somebody, also you can help somebody else. So stay safe. If you have any comments, let me know in the comment section. Otherwise, share the video with your friends, and let's happy Kaggle.